Let's see in chapter 3 what are the main point we need to know. See the weightage, it's the highest percentage, all others are 79, only this one and assets and bases a higher percentage. Okay, so this chapter is very important. Okay, the first part of this chapter actually IMF, and second part you can consider like solution aspects, and the third part you can consider like gas. These are the three part in this chapter 3. Okay, so let's see the first part, IMF. IMF, the most like the stronger, like which one is more stronger, like that the order is very important, right? You may only heard about like or maybe more concentrated with that hydrogen bond, dipole dipole, right? See, this intermolecular forces are the covalent molecule. In the previous chapter we studied like the different kind of bond, right? In which covalent molecule we studied. So in covalent molecule, what are the IMF? That is this hydrogen bond, dipole dipole and dispersion. So in ionic compounds, what are the IMF? Ionic compounds or all other chemical bond, this chemical bond itself is their IMF. Okay, so there is no difference because this kind of molecule like a discrete unit is not present in any other kind of things. So network covalent bond, what is the IMF? Same the chemical bond. Metallic, what is the IMF? Same the chemical bond. Ionic compounds, what is the IMF? Same the chemical bond. Only this covalent bonds, there is a perfect distinction between the chemical bond as well as the IMF. So definitely we are comparing IMF mainly like we are comparing like a physical force. This hydrogen bond, dipole dipole, and dispersion, these are just a physical force. So when you're comparing a physical force with this chemical bond, definitely chemical bond will dominate, right? That's why this is the most stronger IMF. And then second, and then this one is third. And here hydrogen bond, dipole dipole, London dispersion. You can tell only when you are comparing similar molar mass. That's very important. Okay. This order is true only when you are comparing similar molar mass, because LTF, that's the problem. LTF, if higher the molar mass, see, just think about these words. In it's a universal force, it's non-polar. In non-polar molecule, yes, LTF is there. Higher molar mass, higher will be the electron density. That's why they can become high polarizability. They have the higher polarizability. That's how it's higher LTF is posing. Okay, that's the reason. Like higher molar mass is not because of higher proton, because some question be like that. One with the higher molar mass having higher LDF because it have higher proton. No, it's because of electron density, higher electron density. Okay, so that's it. So similar molar mass, then only you can tell this order: hydrogen bond higher, then dipole dipole, and then Lambda dispersion. Okay, so hydrogen bond, how do you know? Yes, you need to just look for OH bond. If any chemical bond contain like OH bond or HN bond or HF bonds are there, then that IMF, that compound can do an hydrogen bond with a nearby molecule, right? Then dipole means you have to think with the polar bonds, if it is a polar molecule or not. And London dispersion, yes, non-polar, then you can think about London dispersion. Okay, this is how we need to know. We are knowing like which one is the, which IMF is they have, right? Okay. Then what's important, like IMF and their properties are very important. If higher the IMF, what's happening? So main thing, if IMF is higher, yes, higher will be the boiling point, right? If IMF is higher, higher will be the melting point. If IMF is higher, lower will be the vapor pressure. Okay. In case of vapor pressure, the gaseous pressure, it will be lower. So what do you mean by vapor pressure? Nothing. It's just you can think about the pressure exerted by the vapors or the gas exerting pressure. So if higher IMF is there, definitely their pressure will be lower, isn't it? Because what is this pressure? Pressure means they are colliding with the walls of the container. That force per unit area is what we call the pressure. So if higher the molar mass, this molecule is actually there is interacted with the another molecule. So they drag literally, isn't it? So that the force colliding with this walls of the container will be less. Okay, if higher the IMF, less force is to the they'll exert to the walls of the container. So lesser will be the pressure. Okay. So that's why vapor pressure will be lowered if IMF is higher. So when you think about vapor pressure, there is a question like can be a question like vapor pressure depending factors. Vapor pressure is depend only on two factors. One is IMF, like IMF is higher, like vapor pressure will be lower. Similarly, temperature. Okay, if temperature is higher, vapor pressure is also be higher. I'm just wanted to say with the vapor pressure because that kind of like some questions are there. Some things are changing, then vapor pressure changes or not like that. So at that time, you can think about only this temperature and IMF can affect with the vapor pressure. Okay, right. See the question, this kind of question you can expect. Which gas has the higher boiling point and why? Hydrogen and neon. So hydrogen is a covalent molecule and it's a non-polar. So definitely in between two hydrogen molecules there is IMF is there, which LDF. LDF will be there. Correct? London dispersion force. Then what about neon? Neon is just an atom. So with a nearby neon atom. So it's both are non-metal. So it is not one to like if it is a metal you can consider like metallic bond. Correct? But neon is non-metal. So this force is actually called again London dispersion force. Okay. So which one is more London dispersion force? Yes, definitely neon. Neon. Why? Is it B or C? Neon because it has more proton or more electron. That's why I'm telling be very careful. It is with a more electron. That's why we have getting high LDF. Okay, then seventh question. Look at the seventh question. Like next question. If the following will change the equilibrium vapor pressure of a liquid. See the change in vapor pressure. So as I told you, it's only depend upon temperature. So heat up, cool, definitely they will depend. And increase the volume. No, and change the pressure above the liquid. That's also no. IMF and temperature will be the thing. Okay, so you can go with the first option. Okay. Similarly, see the question related to IMF. As shown above, four identical containers are there, hold the same number of molecules. So here, the same number of molecules. So number of moles is same, identical containers, so volume is same, and for different gas at 298 Kelvin. So temperature is also same. If ideal behavior is not assumed, usually if these things are constant, according to PV is equal to nRT, P also have to be constant. But PV is equal to nRT only for ideal gas. So that's why they were given pressure is actually not the same. Why? Because they were not assuming ideal behavior. Okay. Then which of the container will have a lowest pressure? Lowest pressure means highest IMF, right? Highest IMF. So which one having highest IMF? H2O, OH bond is there. So in between two H2O molecule, hydrogen bond will operate. CH4, it's a non-polar molecule. Carbon hydrogen bonds are always non-polar. Okay, so that's why you can expect LDF. And this one is also LDF. This one is also LDF. Yes. So H2O. You can go with the H2O. Right. And see the next question. They were given C6H6, C2H5OH. So see the boiling point, C2H5OH. See hydrogen bond, right? This is hydrogen bond and C6H6 is a non-polar thing. So LDF actually. So as I told you, do not blindly believe the order like hydrogen bond, then dipole, then LDF. It's depend upon the molar mass. Okay, so see boiling point is direct evidence. If boiling point is there, you can tell without any doubt higher boiling point, higher will be the LDF. So see in this case 80.2 is the higher boiling point, which means whatever be the IMF present in C6H6, that will be a higher strength. Okay, so LDF present in C6HCX is stronger than the hydrogen bond present in C2H5OH. Okay, so many FRQs are in that way. It's already there. Okay, so many FRQ they were asked. So at that time also use this principle. Boiling point if it given, you do not want to think about any order. Okay, boiling point is a direct evidence. Higher boiling point, definitely higher will be the IMF, whatever be the IMF. Okay, they were asking lower vapor pressure. Okay, lower vapor pressure is for which one? So higher, what? Stronger force. Okay, higher IMF thing contain lower vapor pressure. So definitely you can go with a C6H6. Okay, that's it. That's the first part of like intermolecular force. And solution part, how do you represent a solution? Okay, so NaCl, suppose NaCl is dissolved in water, so the main thing, the size of the ion, they will separate into its ion, so Na plus plus and Cl minus. So which one is higher in size? Yes, Cl minus is higher in size. In periodic table, as we go from left to right, usually size decreases, right? So you may tell like sodium is here and chlorine is there, so you may tell so chlorine is lower atomic size, right? But the problem is here we are comparing ionic radius, not the atomic radius. Okay, anion will be larger than their parent atom. Similarly, cation will be lower than their, smaller than their parent atom. Okay, so Na plus is smaller than the sodium atom. Okay, so while we considering that ionic radius, definitely sodium plus is lower size than the chlorine radius. Okay, so here it's not for look like that, right? Okay, so bigger Cl minus, and then the H2O, right? H2O have to attach with this one. Which atom? As you know, H2O is polar, so hydrogen is partial positive and this one is partial negative. So this is partial positive. Hydrogen is partial positive. This one is partial negative. So oxygen will attach with this sodium cation. Okay, and the hydrogen will attach with a chlorine. So this should be the structure. Like you can do multiple water molecule. Okay, basically this is the thing. Okay, and so what is the interaction? This solute solvent interaction is what this interaction is what we called ion dipole interaction. This IMF is what we call ion dipole. See, one is ion and the other one is a polar molecule. So dipole, ion dipole interaction. Okay, right. After that, you can think about like which of the following have highest conductivity. Like how do you tell which one is higher conductivity? This kind of questions you can expect. At that time, think about highest conductivity means highest number of ions will be there. So AgCl will dissociate like Ag plus plus and Cl minus. So two ions. And AgF is dissociate like Ag plus plus and F minus, but 2 molar is there. So there are altogether 4 maybe. And here here Al2, so this is dissociated like Al3 plus 2 aluminum is there, and then Cr2O4 2 minus is 3 in number. So altogether there is 5 ions. More ion, more will be the conductivity. Usually these ionic compounds are conductive. Right. Then if this is the stuff, how do you tell? HF, HCl, NH3, CH3COH, all of them is molecular compound. If molecular compounds, how do you tell that one? Okay. So at that time, you can think about a strong acid and strong base like that concept. Right? HF, as you know, it's a weak acid. So that much of ions are not produced. HCl at the same time, it's a strong, and NH3 is weak base, CH3COH is also weak acid. So definitely you can go with the HCl. This kind of conductivity things they may ask. Okay, and in this chapter you need to know whether that solubility of ionic compounds, like what are the ionic compounds are soluble. That is also useful in chapter 4, where we need the net ionic equation, right? At that time, need to know this much. At least this much of thing you need to know. Nitrates, whenever nitrates are there, they are soluble. Whenever acetates are there, they are soluble. Whenever group 1, our the like lithium, sodium, potassium, rubidium, cesium, francium, these things are there, their cations are there, definitely they are soluble. And ammonium is there, definitely they are soluble. All these things are soluble. If it's a molecular compound, then use the principle like dissolves like, right? So for example, CO2 or SO2, which is more soluble in water, more soluble in water. So CO2, have to just quickly draw the Lewis diagram. This is the Lewis diagram for CO2. SO2 is, this is the Lewis diagram. So how do you know polar? Central atom with the lone pair is polar. So here lone pair is there. At the same time CO2 is non-polar. No lone pair, so non-polar. Okay. So this one is polar. So polar like polar. So water is also polar. So which one is more soluble? SO2 will be more soluble in water. Okay. That's it. and then the effect, the solution, like Henry's law will be, they may ask, like higher pressure, higher will be the solubility of gases. Only gas we can apply this Henry's law. Okay, and also in this chapter you can study the dilution equation. M1 V1 is equal to M2 V2. Like before dilution, after dilution, the number of moles is same, right? Before dilution, after dilution, the number of moles will not change. And the main thing is separation technique. Chromatography, that's very, very important. Oh, I think I lost the heading. Chromatography. Okay, chromatography. So chromatography, what is the principle? There are two things. One is called a stationary phase and the other one is called a mobile phase. Suppose see, you are taking a glass slide like this. Here you are pasted some coating. Okay, this glass slide, the entire glass slide is pasted with a something. That thing is what we call the stationary phase. Stationary phase. Okay, then then your sample is added at here, right? So sample is what? It's a mixture. It's a mixture of substance. Okay, so what is our purpose? We need to separate this A and B, right? Suppose you are adding some A and B here. What is our purpose? It's have to separate. So this stationary phase coated glass slide with the sample, you are like a drop of sample only, you are dropped into a solvent. So here the second thing, as I told you in chromatography, two things are there. First one is stationary phase and the second one is called a mobile phase. So you have to dropped into this solvent containing beaker. So that solvent will move upward. So what happened? Suppose this mobile phase is polar, then A is also polar and the B is non-polar. So which one will move with this mobile phase? Yes, as you know, like dissolves like. So polar substance in this A and B, polar is A. So A will move with the polar mobile phase. So that will go with this mobile phase. So that will move more distance. Okay. So this solvent, if this much is the thing, like solvent, how much distance they traveled. That is what we call distance traveled. That's the ending point is called a solvent front. So solvent front distance, that should be the bottom, and the top you can write how much distance is traveled by that component. Okay, so see in this case just I am taking like 3 centimeter is by A and the 4 centimeter is by the solvent. So 3 over 4 is what we call the retention factor. Okay, by using this retention factor you can even identify the A and B. Okay, not only just separation, you can identify the sample with the predefined RF values. Okay, right, you can compare this RF correlation chart is there. You can compare this RF factor, which RF factor is matched with this one, like that. Okay, and so see the question from this like separation. See, spinach leaves contain 3 visible dyes: carotene, xanthophyll, chlorophyll. A spinach sample subjected to paper chromatography using a non-polar solvent. See the thing, it's a non-polar solvent. So highest traveling thing is carotene. So that should be non-polar. Okay. If this is, see the this is the solvent front. Solvent front. So the movement is start from here. Solvent is moved from here to here. Okay. So most non-polar is carotene. So see, they have to, like, you have to arrange like most to least polar, right? So carotene will be the least polar. Okay, so which of for the only C option will have carotene is the lowest polar. Okay, so in that way you can identify. Got it? Right. So that's the second part of unit 3. Third part of the unit 3 is nothing, our gaseous chapter. See, you need to know with this gas laws, like they will provide the the sheet, maybe P1 V1 is equal to P2 V2. All others are fractional form. V1 over T1 is equal to V2 over T2, right? All others are fractional form, and you know the STP is 1 atmosphere and 0 degrees Celsius. At STP you can take the advantage, like 1 mole is equal to 22.4 liter, and the combined gas law is there. PV is equal to nRT is there. R value is 0.0821. All the equations are available, And see, this is the density equation. If density, if you want to include, Pm is equal to dRT, like that density equation also you can study. And Dalton's law of partial pressure, you need to know with these two important equation. If mixtures are there, P total will be the sum of individual mixtures, like individual partial pressures, and individual partial pressure you can study like N1, like number of moles over the total number of moles times P total. Okay, that is the fractional number. N1 over N total is fractional number. Okay, right. And the normal KMT you need to study Maxwell distribution of uh, that's nothing like, and KMT, like these kind of things are maybe sometimes confusing. Which of the below gas would be the most ideal? So what is most ideal condition? Ideal condition means, as you know, volume we need to make very high. Volume have to be very high. So if volume have to be very high, then pressure should be low and temperature should be high. So low pressure, high temperature is ideal condition. Okay. Similarly, you can add that IMF also. IMF, like no IMF, isn't it? No IMF. That is what we called ideal gas. So see here, oxygen, water, helium, argon is there. So first you can think about low pressure and high temperature. So which is the low pressure and high temperature? This and this, right? At that time, you can, both of them are same. So you can think about IMF. Oxygen is non-polar, so LDF. Helium is also non-polar, so LDF. So which one is lower LDF? Definitely helium. Helium will have a lower molar mass, so lower LDF. So definitely you can go with the HE. Okay, most ideal. Right. Then similarly, if this kind of question, how do you tell? Under ideal situation, which of the following have higher IMF? So under ideal situation, see what is ideal situation? They are not bothered about IMF. They, according to ideal concept, there is no IMF. So do not answer like NH3. NH3 is hydrogen bond. Other one is what? London dispersion. CH4 is London dispersion. No. Which one is higher IMF? All of them have same. Okay, all of them have same IMF. That's the thing. Okay, and then because an ideal condition, if that clause is not there, yeah, you can think about NH3. Okay, then diffusion and effusion have to study, like main thing, higher the molar mass, lower will be the diffusion rate. It's obvious, right? Lightweight particle can easily move speed. Right. So for example, if this kind of questions, equimolar mixture is there, same number of moles, hydrogen, but even same number of moles, hydrogen, you know, the 2 gram, H2 is there, 2 gram, nitrogen is some 14, so 28 maybe, fluorine I think some 20 something, some 80 or something. Anyway, which is also higher than this nitrogen. 18. So after some time passed, place the gas in order to in order of increasing amount of remaining in the container. So which one is more in container? So which one? Lightweight particle is hydrogen. So hydrogen escape or more effused, isn't it? More effused. So there is very low amount of hydrogen in the container. Then nitrogen and then fluorine. Okay, that will be the thing. And also in gaseous chapter, you can expect this kind of question like FRQ or like that. What's the final pressure in the container shown below? After the valve open, see there is a two gas, like two container is there, one with a nitrogen 2 atmosphere 2 liter. Here oxygen is there 4 atmosphere 3 liter. When this valve is opened, what is the final pressure? So when valve is open means you are expanding, the volume is increasing. So pressure and volume thing is related, all others are same, correct? Pressure and volume is related. So you can think about P1 V1 is equal to P2 V2. So initially on P nitrogen, partial pressure of nitrogen, we can do individually. That's the only way you can do it. Okay. Now, what about partial pressure of nitrogen? Even you do not think like when you are mixing, number of moles is also increasing. The problem is partial pressure of nitrogen is the nitrogen number of moles is same, right? So there is no change in partial pressure of nitrogen in terms of number of moles. Okay, only in terms of volume is changing. All others are constant. Okay, so that's why you can use P1 V1 is equal to P2 V2 in nitrogen case. So 2 is here, 2 is there, and here also P2 means P2 we need to find volume. Now it is this gas is like valve is open, so now the volume is 5 liter. Okay, so altogether P2 will be 4 over 5. Okay, that's a new P2, that's a new pressure of nitrogen. And same thing we can do with the oxygen. So P1 V1 is equal to P2 V2. Here also volume, number of moles of oxygen is not increasing, and the temperature is constant, everything other is constant except the volume. So what is the volume? Again the new volume is P2 5 and the initial one is 4 times 3, right? So now the P2 will be, yes, 12 over 5. So what should be the P total? P total should be, yes, the sum of these two. So in this way you can do this one. Okay, so P2 of like P nitrogen and P2 of oxygen. Got it? This is the second pressure. Okay, that's how, like 4 over 5 plus 12 over 5. This is how we need to do this kind of question. Okay, so that's all the chapter 3 things.